Well, thank you everybody so much for taking the time out of your very busy schedules. I wanted to talk to you today about something that I'm very passionate about. I've spent a career in and out of the military looking at a particular kind of technology that most folks don't think of as digital technology, which means most folks don't think that these things can get hacked. And so we don't talk about the cybersecurity of them too often. And so what I want to do today is broach the subject of what these technologies are, how there are trillions of dollars of these assets around us, and how we as a cybersecurity community, as well as the broader entrepreneurial ecosystem, needs to start treating this as a real frontier of cybersecurity and a huge opportunity, not only for us to make the world around us safer and more secure, but for real business opportunities. So I'll start by getting us centered on what I mean by digital technology and scoping it down a little bit to the things that we don't normally think of as computers. So there are the easy things that are around us that we've known for decades are digital technology, and we think about them as technology, things like cell phones, your iPads, desktop computers. Some things that start blurring the line a little bit between the digital world and the physical world, things like robots. If you've ever seen those slightly terrifying videos of the Boston Dynamics robots doing gymnastics and backflips and things, or the dogs clearing rooms. I think we're getting a little bit closer to Terminator than a lot of us want to admit. But those are fundamentally digital technologies. There's no question about it. There are even evolutions on some of the most important concepts from the Industrial Revolution, things like the assembly line. If you look at a modern assembly line, the devices that are kind of ugly looking utilitarian boxes with a bunch of buttons and ports on them in the top right there, those are called programmable logic controllers, PLCs. Which is a really important initialism in manufacturing. Basically, these devices are responsible for translating messages from computers to physical devices that run things like assembly lines or control different aspects of a water treatment facility or a power plant. These are most certainly digital pieces of technology. There are things that invaded our homes. I know I don't think I could have gotten through COVID with small children without a Roku, but that is fundamentally changed the way that we live our lives, and is certainly a piece of digital technology. And then of course servers. I mean, while a lot of us don't host servers anymore, and we're able to spin up a tremendous amount of computing capacity with the click of a button by visiting Amazon Web Services these days. Servers played a core role in transforming how businesses operate all over the globe. If your business isn't operating software, it's certainly the exception rather than the rule these days. And something finally that I spent a lot of time with in the military is weapon systems, the platforms in the United States Department of Defense arsenal that keep us safe. Things like missiles. Believe it or not, missiles are crammed with microelectronics these days. There are dozens of tiny computers arrayed around things like aircraft, even a Boeing 737 or a fighter jet. The F-35 is a flying supercomputer. It generates terabytes of data. And we think about it as a instrument of freedom that flies around at Mach 2, but it is actually a supercomputer. So all of these things are technology, and when we look at them, I think most people would recognize them as such. But there's an important distinction that's emerging among business leaders and the technology community, and that is this distinction between what we call information technology, IT, a term that is in household use, and operational technology, which is something that maybe you've heard of, but isn't something that's widely known or acknowledged. And the distinction is this. So when people talk about information technology, they're thinking about those things like iPads and cell phones and laptops and servers. that are there to store, aggregate, and expose data. And what you do with that data is you make business decisions. You use that data so that you can optimize the way that you run your business, or so that you can run your payroll, or any number of permutations of these ideas. But fundamentally, you're just moving little bits around, little electrons around that store and manipulate information. On the other hand, operational technology is kind of this category of technology that doesn't really fit that description. It's almost defined as a complement to IT. And so some people say that it's there to basically conduct business operations, which is a bit of a circular definition. So we'll try to do better. And operational technology, when you think about it at a more fundamental level with respect to IT systems, where you say, okay, well, IT systems are there to manage and store and manipulate information. Operational technology is there to monitor or alter the physical state of a system. That system could be, like I said, a manufacturing assembly line. It could be a missile that's on the rail of an F-18 Super Hornet. It could be a programmable logic controller. All these sorts of things. So you sort of know it when you see it in an OT system. And I'll give you a couple of clarifying examples here. So one of them is what the industry calls ICS and SCADA. That stands for Industrial Control Systems. But basically, you see these things all over very large industrial applications. As I mentioned, something like a nuclear power plant is a prime example of an ICS SCADA system. Something I spent a lot of time around, ground combat vehicles. These things are giant, terrifying vehicles with big guns on them, but they also have a dozen or more electronic components in them that help the crew inside of that vehicle do its job. Perhaps again, in the more terrifying category, the Army has a multi-billion-dollar program on the horizon that's called the Optionally Manned Fighting Vehicle. Which is kind of scary when you think about it, that you may optionally have a person behind the turret of a tank. But we're getting there to the point where you're going to remote control these things because the personnel inside of them are extremely precious. Mining equipment. So you see there a giant earth mover. These things are responsible for tens of millions of dollars of revenue generation on a monthly basis per unit. And they are giant computers. They've got control systems in there that make sure that in various kinds of fail states that they operate in a safe way, that they're burning fuel efficiently, that they're detecting maintenance issues and reporting those to the crew. Lots and lots of technology on there. We talked a little bit about aircraft. That's an F-35 there breaking the sound barrier. Generates terabytes of data per flight. It's just truly incredible. And they even have network capability where they can transmit data between themselves to create a sort of mesh network. It really is amazing science fiction that we're seeing today. Things that some of you may even have installed in your homes, things like IoT devices or sous vide machines or garage door openers. These things are getting wired into your home network and phoning home to a web service for your convenience, so that when you drive home, your door unlocks for you. Or if, in my case, my 3-year-old likes to unlock the door, it makes sure that it locks it after 2 minutes. That there are tons of technology in these things. Building automation, cars, watercraft, you get the idea here. All of this stuff is crammed with technology because it just makes economic sense for the manufacturers of these devices to do it. We put digital components in here because it's cheaper to manufacture them. You get more flexibility, you get more features, and it makes you more competitive in the marketplace. So some important things have changed though, and what you're looking at here are called integrated circuits, and they are a modern marvel. They contain billions of transistors, these tiny little switches that, in my humble opinion, are probably the most impactful invention in human history. back in the day, so 30 plus years ago, maybe 20 plus years ago, these integrated circuits were fixed. Okay, so you can think of them as a system, a machine, a digital machine that when you apply certain inputs to it, it creates certain outputs, and those inputs and outputs are known and fixed. Okay, you can't change them. So that's on the left there. You see an integrated circuit where if you know what you're doing and you apply electrical voltage to certain pins in certain timings, it will produce certain outputs as a result. And for the longest time, technology, the digital technologies that we talked about in the last slide, contained dozens or hundreds of these integrated circuits that are wired together on those printed circuit boards, those green boards that made of silicon that you're used to seeing. And there's a quiet revolution that happened over the past, call it 15, 20 years, which is on the right here, you see a PIC microcontroller. So they may look basically identical. And here's the difference. The one on the right is called a microcontroller, and it runs software. So I can take code, instructions, and I can upload that code into this circuit, this microcontroller, and fundamentally change the way that it behaves, okay? And it seems like a small difference, but it makes a massive, it completely changes the game. Because now, things that required me to design these circuits, which is a kind of rarefied skill set, it's slow, it's expensive, you have to put lots of integrated circuits together, there's more parts to where it could fail. I can lift all of that up into software, and now all of a sudden I've got this tremendously flexible little tiny computer that can do all of these things. And so it has absolutely taken the technology world by storm, these microcontrollers. And it has really important ramifications. So I figured no good pitch from a venture-backed startup is good without a Mark Andreessen quote. So software is certainly eating the world. I think he intended for that to be pointed at businesses, but it's also eating the world of integrated circuits. And the result is that it's making everything vulnerable to cyber attack. So whenever you have software in something, it means that a hacker can try to take control of that thing with their code, right? It opens up an attack surface. And so the thesis here with this talk is because we've migrated from integrated circuits on a lot of this technology into microcontrollers, into things that you can update with software, it creates this whole access vector of where you're able to attack things that previously didn't have attack surface before. They were too dumb for a cyber attacker to be able to do anything meaningful to it. And so I'm going to go over two different classes of operational technology and outline for you, just give you a little bit of an imagination for what could happen if an attacker who knows a thing or two about operational technology wanted to do something really nasty and subvert operational technology by using a cyber attack. So we'll talk a little bit about what these ICS systems look like at a very high level. So if in the top left here, you see a very technology-enabled assembly line here. There are a lot of robots. There are lots of electronic control units, and basically the idea here is that the returns to labor from this capital are tremendous. You can have one or two people overseeing this facility, and it can generate a tremendous amount of a highly customizable product as a result, right? Because there's so much software and control systems in here. At the heart of a lot of these control systems is the thing that's in the top right there. It's a programmable logic controller. And so this thing is, as its name implies, programmable, which means that you can upload software to it and change the way that it operates. So you can see where these things are, where this is going. If an attacker is able to either trick the programmable logic controller to run its own code or fool its inputs and outputs, you can create really devastating results out of it. So here's a kind of it's a little simplified, but it's a reasonable representation of what an enterprise might look like that has operational technology. So again, this could be, a manufacturing, a company an OEM that manufactures thing. It could be a power plant or oil and gas operation or something of that nature. So if you walk through how these things are connected from the top, you've got the outside world, which is, the internet. You've got a router and a firewall in front of the internet, and that's where all the traffic goes through the corporate network, where you've got all of there's this terminology of where the floor is carpet or the floor is tile, and for the workers that work on carpet in the corporation, the knowledge workers that use IT to do their job. You've got workstations, printers, application servers, cell phones. You've got video teleconferencing solutions. It's a soup of IT stuff. Typically, you'll have some control measures, some kind of static set of rules that separates the corporate network from the control network, from the operational technology, the parts of the technology stack that do the business that business is in. You'll have what they call data historians. So this stores all of the data for what's going on in that OT network. And then you have what up until very recently was just a wild west of programmable logic controllers, human machine interfaces, which are just computers that are allowing people to control the industrial system that they're responsible for, and then some set of servers, in that control network. So if I'm an attacker and I look at this system and the connections between these things, my goal is that I want to take over those programmable logic controllers. One mental model that you may be useful here is if you've ever heard of the Stuxnet attack. This was an attack on Iranian nuclear material enrichment, and really sophisticated attack where the attackers went after the operational technology, and they were able to set Iranian nuclear ambitions back by like a pretty, people argue about it, but probably years. And so if I'm thinking about those kinds of attacks, I've got all kinds of attack vectors here. So one is I try to get physical access. Okay, you would be surprised how with a clipboard and a vest, you can get into pretty much anywhere. If you tell people that you're there to inspect for safety and you've got a hard hat on and you have a stern demeanor to you, you can get into most places. And so physical access isn't nearly as hard as it seems in a lot of contexts. So if you can get physical access to these PLCs, there's no security on any of them. You get 5 minutes of access. You can plug a computer into one of these things and you can put your own code on it, and you can see how bad that could be. Another option is sometimes you can design custom devices, but you can make tiny little devices that you can leave behind and connect to the Ethernet network, for example, and do things like spoofing signals to give rogue commands to these PLCs for them to open up a floodgate or close down in a critical condition and cause some really devastating damage. Another one that came up was supply chain attacks. So these are really, really, really terrifying and very hard to detect, and they can happen on a lot of levels. So one level is hardware supply chain attacks. So regrettably, a lot of the microcontrollers and integrated circuits that are in use around the globe today come out of Shenzhen, China, right? Because there's a real community of excellence and expertise about developing there. There's low labor costs, and it just makes economic sense for people to outsource this kind of commoditized service to China. Well, supposing they're an adversary and they want to get code into some particular critical infrastructure in the United States, you can see how this could go very badly. There's also supply chain attacks on the software side, which is what we saw in SolarWinds. So A lot of these PLCs will require regular firmware updates, software updates from the manufacturers. And I think a frontier of cybersecurity that's opening up is vulnerabilities in open source software that all of us in the technology industry depend on. So modern software, when you make it today, you're really, it sounds weird, but you're really just stitching together code that other people have written. That's a lot of modern software development. You know, you want to write an app, you're not writing a database from scratch. You're not writing a web server from scratch. You're not writing so much of the code, all the algorithms for sorting and this and that and the other. You're pulling third-party dependencies down to do that work for you, and where the innovation is in how you're stitching those dependencies together, right? Those are the raw ingredients, and then how you put them together and season them and cook them is the art of building software. Well, if that's the state of software, it turns out there's a huge attack surface in all of those things that you're pulling in, because I guarantee you, based on real evidence that's out there on just how much malicious third-party software you see on open source software repositories getting removed every month, this is happening, right? And we're going to see more and more examples of people pulling third-party dependencies in and unwittingly distributing malware to their customers. And so that's a very viable attack vector to get into one of these PLCs, for example. There's also an issue of what we call in the business pivoting. And so this is a really, really nasty, we saw this in the SolarWinds attack. We see it in so many of these APT, these advanced persistent threat reports that you read about. An attacker will get a foothold somewhere, and then they'll move around using various techniques. So when you hear about phishing, the theory for most attackers is, hey, I'm going to steal some credentials, a username and a password from an unwitting insider, and then I'm going to use those credentials to masquerade as that person and do some real damage. And if I'm careful about it, if I'm patient, and I have good operational security, it'll take on average 9 months for a defender to realize that I'm in their network, and then I'm moving things around. It's really really upsetting statistic, but it's true. And so it's possible for me to phish credentials to get into one of these data stores, and then pivot around from there to try to achieve the effects that I want. You know, one of my in a previous life, one of my favorite targets was the IT system administrators. And it's not because they're not savvy, it's because they have the deepest access into the system. No one questions really when an IT administrator is doing routine maintenance to shuffle things around or clean up some logs or add users. And so it's disconcertingly easy for me to go from a corporate network and then swim upstream to the control network and do some real damage and cause some damage in the physical world. Finally, you've got these routers. So, you know, these things are just out on the internet. And so there is a service called Shodan, SHODAN. There are a couple of these services, but basically they scan the internet. There are 4 billion or so IP addresses, and they'll just scan all of these IP addresses for services that are either misconfigured or they have default passwords. And you would be, maybe you wouldn't be, but I'm consistently surprised at just how much unsecured stuff is just out there hanging out on the internet. And so this is a really lowbrow attack. You don't even need to craft a fancy email that says, hey, here are the 2020 bonuses, just open this Excel file, or sprinkling USB drives around a parking lot to hope someone plugs it in. Sometimes you can just go right in through the front door and do some damage from there. So ICS and SCADA systems, just a comment on the market, which this is a very interesting frontier of cybersecurity that has gotten a lot of attention recently. There's a lot of venture dollars that are going into ICS SCADA cybersecurity companies. A couple of them of note are Dragos, Clarity, Nozomi, There are also some of the big publicly traded cybersecurity players that are acquiring companies to add ICS and SCADA to their portfolio. I think and by the way, we're seeing lots of ICS and SCADA attacks that are all those arrows in that diagram in the last slide. We're seeing attacks along all of those access vectors. And so this is a really critically important thing for us to do for national security. You think about power grids going out for days, or water getting contaminated, which is not theoretical, has happened in Israel, or manufacturing of critical things going down. I mean, you could cause some real damage in the physical world if you're not watching out on your ICS and SCADA. Something that's near and dear to my heart, and what I think is a bit more of a early stage cybersecurity frontier, is what are called fleet assets. So fleet assets are things like locomotives or aircraft or military weapon systems that OEMs, original equipment manufacturers, will design once, and then they'll make many copies of. And unlike an ICS and SCADA system, which is they're each like little snowflakes, they have some similarities between them, but they're fundamentally different from one another because every control system is different. It's customized to the business of the operator. But these fleet assets are more or less identical to each other. And they contain, as we were talking about, dozens of little electronic control units and sensors and actuators that do the work of operating that asset. So you think about a tank, for example. There's a targeting computer that automatically, you just you put a little dot on the thing that you want to shoot with that 105 millimeter round, and then you click a button, and a whole bunch of windage calculations and trajectories and ballistics go into what actually happens and where the tube is oriented, and all that happens in software. The engine itself is controlled by electronic control units. There are ECUs all over that thing. So you think about there's a turbine engine in a tank, and it actually is disconcertingly difficult to keep a turbine engine from blowing itself up. And so you have to constantly be adjusting the guide, the inlets, and all these different surfaces and flaps to keep it from exploding, basically. And then, of course, things like radios and update displays that the commander of the tank use to have situational awareness. Something a bit less unusual, and something that you probably interact with in your daily life is a car. And a car has dozens of electronic control units all over it. You think about, again, the engine control unit, but your anti-lock brake system and drive-by-wire. Most vehicles these days, you're not actually pushing down on a wire with your gas pedal that's opening up an inlet. It's actually a sensor that is transmitting electronic signals to tell the engine that it needs to increase its power. So these things are all over the place. All these fleet assets, and they are networks of computers. There's also a critical component to a lot of these, the more expensive ones, which is maintenance devices. So if you ever noticed you brought your car into the mechanic when the check engine light came on, and they plug a computer in to your this port on your car called the OBD2 port to download maintenance codes, that thing is getting root access to all of the electronic control units on your bus. So you are really trusting that technician when they plug things onto your car, because if it has malware on it, as you can imagine, it could do some real damage. So how do you attack these things? Well, a lot of the attack vectors are pretty similar to ICS and SCADA. These LRUs, these line replaceable units or engine control units, are susceptible to supply chain attacks. So you can get malicious components onto these, or upload put software that's malicious on them. It's pretty straightforward. There's also hardware implants. So these things are pretty large, and it's easy to hide a tiny little device that's half the size of a credit card onto one of them. So It might seem like an obscure thing that someone might get physical access to a tank, but it's easier than you think, especially when we're flying these things all over the world, and they're getting offloaded by foreign nationals because that's what's in the status of force agreement. But I digress. One of the harder targets, but nonetheless an access vector, is there's a lot of radio RF stuff that's coming on and off of these systems. And so this could be really devastating, right? If you think about some sort of remote access vector where you transmit a particular kind of code and you're able to do some real damage and potentially pivot through a radio system. Right. Locomotives are they're not dissimilar from something like a tank. Okay, same kinds of components on them. It's a very large asset with a big engine that's moving things through space and time. And for various reasons, including government regulation, these locomotives are installing systems onto these control buses that have remote access, installing either getting access to the IT side of things, like I was talking about, and swimming downstream from there, or just looping into some of these systems where you've got remote access vectors onto a locomotive, and you could cover a substantial portion of a fleet within, say, a couple of weeks, right? By just being patient and accessing these things through either remote means, or if you were able to attack the IT side of things and then move from there. And the effects could be just absolutely devastating. At the very least, it's fairly straightforward to cause denial of service, right? So we just saw on the IT side there was a company called Omnitrax. It's a short haul freight operator that just got nailed with a crypto locker malware, which is like lowbrow, indiscriminate kind of attack, but it caused real substantive business harm. Imagine if attackers were slightly more sophisticated and instead of using general purpose malware, launched a more concerted campaign against a Freight One operator and held 1,000 of their locomotives at risk and said, hey, we've got malware on your locomotives. We're going to demonstrate this on 10 of them that they're just not going to start, and we're going to tell you what the numbers are. We're going to do this systemically unless you pay us $50 million. It's hard to point fingers at the designers of these systems because no one ever really thought about the cybersecurity of ICS, SCADA, or fleet systems, or just OT in general. People designed these systems and protocols for reliability and robustness in the physical world, not with security in mind, not with the idea that there's a witting adversary, there's a human being on the other end that's actively trying to subvert this system. And so, the result is we're in this world now where all this stuff is vulnerable. And I'll kind of go quickly through this to give you a sense of just how easy it is to get started hacking these things. There's a really important protocol in this world called CAN. It stands for Controller Area Network, and Bosch invented it in the 1980s for their Mercedes-Benz vehicles because they realized that they could bring integrated circuits into a car and save a lot of money because these things are cheap to manufacture, and the flexibility that they give over analog systems is tremendous. So this is what CAN looks like. If you pulled out an oscilloscope and you looked at it, it's really crude. You have voltages that go in two different directions. And so all of the components on the bus just see this kind of step function of electrons going across the wire, right? There's no security in this thing. So basically, if I'm on that bus, I can change what everyone else is seeing, is the long and short of this. And so that percolates up into zeros and ones that mean things to the control units that, for the electronic control unit that governs the engine, for example, it's going to see 0010101, and that means, oh, I need to be at 7,000 RPMs. Okay, so if I get on this bus and I transmit zeros and ones and stomp over what everyone else is doing, I own the bus. okay? This is how these systems were designed. This isn't a vulnerability, this is a feature of the system. And it is not that hard to make devices that can do this sort of thing. And so what you're looking at is there's a wonderful microcontroller that's called the Arduino. And if you have any interest in, people pick up weird hobbies in COVID, baking bread, cocktails, why not learn how to program microcontrollers? For $20, you can buy an Arduino and you can make a device that could hack a car, right, with $20. And you're looking at the setup right here. So this here is a Caterpillar C7 diesel engine. And this is found in a lot of really important devices. We found an engine control unit, that like kind of squatty mustard color thing on the left-hand side, on eBay for $700, okay? So if we're able to do this for $700 with access to eBay, you know that adversaries are able to do this, okay? So what we did is we took this engine control unit and we wrapped it into a demo where we're able to simulate a full engine and then demonstrate a pretty straightforward cyber attack that could have devastating consequences. So I'm going to share with you a video that we've pre-recorded of this demonstration. This demonstration comprises 6 components. A Caterpillar C7 engine control module, which collects sensor data and controls actuators on the engine. A Shift5 software-defined engine, which convinces the engine control module that it's connected to a real engine. A CAN J1939 bus that the engine control module uses to communicate with other electronic components on the operational technology platform. Shift5 intake and engine on a rail-certified commercial off-the-shelf hardware, which records, transmits, and analyzes all J1939 traffic and alerts on anomalies. A remote-enabled hardware implant, which is armed with a payload that overloads the engine control module and completely shuts down the engine. And finally, a battery pack that powers the demo. The Caterpillar C7 engine control module is the brains of the engine. It collects sensor data and controls the actuators within the C7 engine. Its job is to ensure optimal engine performance. Roughly speaking, it reads values from the sensors, performs calculations using lookup tables, and adjusts the engine's actuators. For example, it controls air-fuel ratios, the idle speed, and variable valve timings, as well as the intake and exhaust valve openings. The engine control module interacts with other electronic components in an operational technology platform. It publishes important data like engine operating status, select sensor readings. All of this goes on the CAN J1939 bus. Also, it subscribes to the sensor data and commands on that same J1939 bus from other electronic components. Shift5 software-defined engine convinces the engine control module that it's connected to a real engine. Engine control modules will not operate if you simply apply power to them. You'll need to feed real or simulated sensor data into the engine control module, and additionally, you'll need to emulate the electrical characteristics of the actuators that are connected to the engine. If the sensors or actuators don't perform within the expected bounds, the engine control module will broadcast error codes. Shift5's software-defined engine contains an array of integrated circuits and microcontrollers that effectively simulate the sensors and actuators the engine control module expects. For demonstration purposes, we've installed several gauges that output the sensor values that the software-defined engine is simulating. We've also installed 6 lights which correspond to the engine control module actuating the engine's cylinders. The CAN J1939 bus that the engine control module uses to communicate is the main communication lane for all the electronic components on an operational technology platform. CAN buses are simple, robust communication networks for microcontrollers. All you need is 3 wires, CAN high, CAN low, and a ground, for all the electronic components to send messages to each other. These buses are broadcast networks, so when a component sends a message, all the other components on that bus get that message. Other devices you might find on an operational technology platform include control modules for powertrain, transmission, brake, timing, suspension, doors, batteries, and telematics. Additionally, human-machine interfaces often participate on the CAN bus. For this demonstration, we've connected the engine control unit, the rail-certified computer running Shift5 intake and engine, and our hardware implant to the CAN bus. We've included a remote-enabled hardware implant, which is armed with a payload that overloads the engine control module and causes total engine failure. The CAN J1939 protocols have absolutely no built-in security, no confidentiality, no authentication, and no integrity. Further, the engine control module is a special-purpose computer, and it runs software. That means it's vulnerable to cyber attack. Once an attacker compromises a device on the bus or installs a hardware implant, they can wreak havoc on the platform. For demonstration purposes, we've wired our hardware implant to a button, which when pressed, transmits legitimate message traffic over the CAN bus, but which causes the engine control module to fail. These systems are highly trusting, so developing a devastating cyber attack like this isn't particularly difficult. An attacker with a basic understanding of engine control modules, a Raspberry Pi with a CAN hat, and a pot of coffee could replace this sort of effect in short order. We've installed Shift5 intake and engine on rail-certified commercial off-the-shelf embedded platform, which records, transmits, and analyzes all J1939 traffic and alerts on anomalies. Our software runs on a wide range of platforms. This demonstration showcases a commercially available, rail-certified, embedded, industrial computer running intake and engine. It has a single onboard CAN interface as well as a 4G LTE network connection. Shift5 intake works on a wide range of protocols, including Ethernet, CAN J1939, Military Standard 1553, RS-485 and RS-232, ARINC 429, as well as some others. This demonstration illustrates Shift5 intake collecting CAN J1939. Intake collects all J1939 messages, records them to disk, and transmits them over 4G LTE to Shift5's data intake pipeline. Shift5 engine analyzes the full take packet capture and alerts on anomalies. No good cybersecurity demo is complete without a blinky light, so we've included this one to indicate whether Shift5 engine has detected any anomalies. Green means good and red means bad. We're ready to launch our cyber attack. After pressing this button, our hardware implant will transmit malicious traffic that will cause the engine control module to shut down indefinitely. You'll notice that the gauges and the lights connected to the software-defined engine have shut down. Shift5 engine has alerted on the cyber attack, and our blinky light has turned red. Finally, I'll press the reset button to stop the hardware implant. You'll notice the engine control module spring back to life, and software-defined engine's gauges and lights will resume normal activity. Shift5 gauge cluster is the customer's touch point into their data. Let's take a look at what the operator sees. After signing in, we launched our dashboard. Shift5 customers can completely customize this interface according to their operational needs. We've built several graphs to enable quick checks on this C7 engine control module status. First, you can see engine RPM over time. You'll notice that there's a period of missing data. Likewise, there's a big gap in fuel injection level over the same period. There's also a big spike in message count, as well as alerts corresponding to this period. We can see that there's an unauthorized PGN which triggered the alerts. This is a J1939 concept, which basically means there's a certain kind of message going across the bus that we didn't expect to see. An operator could quickly identify that something's awry. The incident responder could dive into the full take packet capture and locate the packets that are causing the engine failure. Let's zoom into this interval to take a look at the packets on the bus during the attack. Taking a look at this data would enable an incident responder to collate multiple feeds of data to determine what happened and how to remediate the situation. For this demonstration, we used a tiny radio-enabled hardware implant that launches a simple but devastating cyber attack against the Caterpillar C7 engine control module. We used Shift5's product suite to detect, alert, and conduct an incident response on this cyber attack. There are millions of operational technology devices in use today. Shift5's mission is to secure all of them from cyber attack. If you have any questions, please reach out to us at info@shift5.io or visit our website, shift5.io. Thanks.